So first I would like to thank the organizing committee for inviting me. It's really a pleasure to be here. And so today I'm going to talk about a work I did about 3 years ago actually, but I've never presented it in Brazil, and I thought this was a nice opportunity to show it to you. So most of this work is joint work with Rafael, who's also from the Federal University of São Carlos. And the application part is joint with Peter Freeman and Lee from Carnegie Mellon University. So the problem I'm going to talk about arose when Jeff Newman, who's an astronomer from University of Pittsburgh, he contacted us and he had a data set called CANDELS, which consisted of images of galaxies observed using Hubble telescope. So it had lots of images, each image of a single galaxy. And galaxies can have different shapes. So for example, there are spiral galaxies, elliptical galaxies, irregular galaxies, and many other morphologies. And morphologies are a very useful source for astronomers to understand the evolution of the universe. And well, one of the reasons is because there are several cosmological theories, and they predict that the evolution of the universe is in a given way. So at that time, there will be that many galaxies of this kind. And if you look close to the Earth, there will be many galaxies of the other kind. And so by looking at the theories and comparing them to what's observed in nature, you can make inference about the evolution of the universe and rule out some of the theories and emphasize other theories. Okay, so it's very useful for astronomers to understand these evolutions. So the question, well, one of the questions Jeff had was, how can you classify millions of images of galaxies? Because Hubble collects thousands of new images every day, and he wants to classify all of them. So in principle, that's easy to solve, right? You could just get a small training sample with, say, 1,000 or 2,000 galaxies, manually classify all of these galaxies. So you ask astronomers, oh, which morphology does this galaxy have, and so on and so forth. And then use your favorite machine learning technique to build a classifier. Okay. But the problem, or one of the problems Jeff had, they actually had this data set. They already had a data set with 1,600 galaxies that were classified by astronomers. But one of the problems they had was that astronomers do not always agree on the classifications. So in some sense, there's a lot of noise on it. And one of the reasons for that, the main reason, is because the images we had from Hubble, they didn't look like that. They were actually like this. The resolution is very, very bad. And that's because the galaxies are very far from us. So it's very hard to say what's the morphology of each of the galaxies. So if you look at the data set, so this is a subset, it looks something like that. So here are 5 galaxies. And there are 3 astronomers, A, B, and C, and they are answering the question, is this galaxy irregular, yes or no? And you see there's a lot of disagreement, okay? So what were the astronomers doing? They were using majority rule to infer the true labels of this data set. So here the first galaxy would be considered to be irregular, this wouldn't be irregular, this wouldn't be irregular, and so on and so forth. And then they would use these inferred labels as the ground truth and use traditional machine learning techniques on these labels, okay? So they would do model selection, everything using these labels. And Jeff was concerned if this was a good procedure here. And there were a couple of reasons for that. So the first one is that there were not many annotators for each galaxy. So there were usually 2, 3, or at most 4 annotators. So using majority rule maybe was not something very good because there was a lot of noise. Second, there was at least one disagreement in about 70% of the samples. So this shows how difficult the problem is. So there were so many disagreements that maybe taking the majority was not something good because there were only 3 astronomers. And finally, and maybe most importantly, there were many different, they expected different annotators to have different expertise. And that's because many astronomers were not from this field, so they were not sure that these astronomers were really well trained to do these classifications. So they were not sure if they should just give the same weight for all the astronomers or if they should be weighted differently. So what we did in this work is that we proposed a Bayesian crowdsourcing model that takes these issues into account. And of course, we did this model for this, to solve this problem, but there are lots of different problems where it can be used for. So to get to the notation here, so we assume, okay, we have a data set with n galaxies, so each row is a galaxy. These here are the true labels of the galaxy. And for simplicity, I'm considering that these are either 0 or 1. So for instance, the galaxy is irregular or it's not irregular. It's a disk or it's not a disk. So it's only one of the morphologies, yes or no, okay? Then there are the experts labels, which are the noisy versions of these. So there are the experts, each column here is a different expert. And the Y then is the expert's guess, are the expert's guesses about Z, okay? And then there are K features, K covariates, which are covariates we extracted from the images. So we got the images, we computed a lot of summary statistics that are used in astronomy, we developed some others, so there are K features here. And our goal is to build a classifier with that can make good predictions, because they are really interested in classifying the samples which are not on this data set, new samples. So this is our goal, and more formally what we want to do is to build a function that has a domain here on the feature space, and whose image is 0 or 1, if the galaxy is or if it has that morphology, or if it doesn't have that morphology. And what does it mean to build a function f, a classifier f, that has good predictions? What it means is that we want f, when applied to m new samples, to recover the z's with high probability. We want it to get the labels right. So a reasonable goal here is to find an f that makes a small proportion of mistakes on these m new samples, right? So we want the average of the indicator function that f is making a mistake to be as small as possible. So of course that's a hard goal because we don't know the z's and x's ahead of time, but by the law of large numbers, we know that this is approximately the expectation of the indicator function that we make a new mistake on a new sample. So we want this, which is the probability of a mistake, to be as small as possible. And this is what I'm calling the risk function of f. Okay, so we want the risk to be as small as possible. Now, there is one catch here, which is the risk is a little bit different from the traditional way we think of risk in statistics. What's random here is the new sample, x and z. Okay, so this is a conditional risk. It's conditional on the sample we've observed. So f is not random. So that's a little bit different from what people usually use. So it's a conditional risk. So this is a frequentist goal in a sense, but it makes sense to me here because we are really going to repeat this experiment of observe new samples many and many times. So it does make sense for me to minimize this risk to find an f that has a small risk. Okay? And that's a traditional machine learning setting, except that we are working with the conditional risk. Many times people don't do that. But what's different is that the z's are never observed, right? We never observe the true labels of the galaxies. So it's not trivial if we can split the data as training and testing to estimate the risk or something like that. And I'm going to talk about this later. Okay, so that's the difference. So the two questions we try to answer in this work, which are related, are first, how do we build a classifier? How can we find a function f that has a small risk? And for that, we're going to use a Bayesian model. And the second question is, say you have 10 different classifiers. How do you pick the best classifier on this class? How can you find the classifier f on this class of 10 classifiers that has smallest risk? Okay, so that's what we are going to address on the second part of the talk. So the outline of the remaining of the talk is that first we're going to discuss our model. I'll briefly discuss how we can fit it. Then I'll switch to the second part and discuss model selection, show some examples, and then go to the discussions. Okay. So our model is very, very simple. The first part of the model states essentially that the probability that the label of a sample, or the label of a galaxy is 1, given its covariates, it's a logistic regression. Okay, so that's just standard. The difference, of course, is that we never observe disease, but we are going to deal with that later. The second and most interesting part of the model states that the probability that that expert K makes a mistake when classifying galaxy I is also given by a logistic regression. Okay, but of course the coefficients here of the logistic regressions are different, and what this is saying is that some galaxies are harder to classify, some galaxies are easier to classify. It depends on the covariates. So this is what this part of the model is saying. And also the intercept of the model is different for each expert. Each expert can have a different expertise, and that's associated to the coefficients alpha. So if alpha is very large, it means that the expert has a small probability of making a mistake. If alpha is small, he has a large probability of making a mistake. Okay? So this is essentially our model. So similar frequentist models have been used. So the first one I'm aware of is from David and Skin in '79, although they didn't have covariates, but the idea is more or less the same. And then in recent years, there was a boom in machine learning literature on models like that. So there are several variations using different links and some non-parametric models. There are several different variations. But they were, at least at that point, when we did the work, they were all frequentists. So what we did that was different is that we wanted to include prior information here. And we really wanted to include meaningful prior information because we wanted the prior information to improve the classifiers that you would get without prior information. And what was the prior information we used? It was essentially, well, there were two parts. So the first part is that for some morphologies, we expected some of the covariates not to be informative about those morphologies. Okay? So we expected some of the coefficients of the logistic regression, the first logistic I stated, to be close to 0 or 0, okay? And the second part of the prior information we used was that we expected some covariates not to be informative about how difficult it is to classify the galaxies. So we also expected some of the coefficients of the second logistic regression to be close to 0. So this is the prior information we used. It's basically a Laplace prior for the coefficients of the logistic regression centered at 0. Exactly because we believe that many covariates are not informative about the responses. And we have a hyperparameter here, lambda, which is essentially the precision of this prior. Okay, so if lambda is very large, it means that we are very certain about our prior information. Okay, so the coefficients should be really close to 0. And for the intercepts, then we use just a flat prior. So that's a very informative prior, right? Now, to fit the model, all we want to do is to get the posterior. So here we can't get an easy analytical expression for the posterior. So what we work with the augmented posterior, which is much easier here. So we sample from the augmented posterior, including the Z's here, the unobserved labels, which is our missing data. And for that, we can use a Gibbs sampler, which is very easy in this problem. So just to give a quick idea, the posterior of the labels, given everything else, is just a logistic regression. That's what I stated before. So we can sample from it using a Bernoulli, sampling from a Bernoulli with different parameters. And for the second part, the posterior probability of the parameters, given everything else, we used an MCMC. We adapted an MCMC from this paper, from Gramsci and Paulson, in which they propose an MCMC for logistic regressions with Laplace prior. So we have to do some tricks, but we can adapt that and use their R package, in fact, and then it's pretty easy to do the Gibbs, and this MCMC, and then do the Gibbs. Okay, so it's very easy to sample from the posterior. Once we have the posterior, to do predictions, we can compute so we have a new galaxy with covariates xn plus 1. We want to find its label. So one way of doing that is by computing the expectation of the label given everything we know, the new covariate and our data set. Okay? So if we work out the details, we get this expression, and we can approximate this using the MCMC. Now, I have to say that the MCMC is kind of slow, so if you want an approximation for that, which is faster, and it's actually what we did for most of the work. You can approximate this by just evaluating this probability on beta hat, where beta hat is the value that maximizes the posterior. It's the mode of the posterior. Okay, so that's just an approximation, but it's much faster. And it's faster because instead of using the MCMC, we can actually use a MAP-YAM. It's a maximum a posteriori expectation maximization algorithm. So it's like the YAM algorithm adapted to find the mode of the posterior. And we can do some tricks, and it works out. It works that in a very nice way. It's very fast. So actually, what we did to do predictions was to use these probabilities. Okay. Now I just want to make a parenthesis, which is that the value of beta that maximizes the posterior is the value of beta that maximizes the log likelihood minus an L1 penalty on the parameters. Okay. So this is just like the connection between Bayes and Lasso. It's the same connection we have here. So in a sense, I see this as a frequentist prior information. Okay, so it's if we could motivate our model just using this if we were frequentists. So it's a place where Bayes meets frequentists in a sense, or it's subjective frequentists. I don't know. Okay, so summary so far: we have a model for the data, we have an informative prior distribution here. Using Gibbs plus MCMC or just MAP-YAM, we can either sample from the posterior or get the mode from the posterior, and then we can make predictions by checking if the posterior probability that the label of a galaxy is 1 is larger or smaller than a half. Okay, and so this is the final classifier we get. I'm calling it F lambda, and I'm using the lambda here to emphasize that it depends on the prior hyperparameter. So for each prior hyperparameter, you have a different classifier. Now the question is, how can we choose the prior hyperparameter lambda? Okay, so now I'm going to switch to the second part of the talk and discuss model selection. So if we are subjectivist Bayesians, we could use prior elicitation and somehow get our value of lambda. But for this problem, I think what makes more sense is to find a classifier that leads to good predictions. Okay, because that's what I wanted. That's what the astronomers want. They don't really want a model that reflects our uncertainty. They want good predictions. And so maybe a reasonable way of defining what's a good classifier here is to find the lambda which leads to the classifier that has smallest risk. That's what I argued before, okay? Because we are interested in the predictions. So what we did in this second part of the work was to answer a more general question, which is given a set of models big lambda, which are indexed by this lambda. It can be models that you get using different priors or different likelihoods, any models you want. How do we find the model that has smallest risk? So what's the standard way of doing that? The standard way is to split the data into training and testing. And then using the test set, you estimate the risk function. So for each classifier, you estimate the risk of that classifier by looking at how many mistakes our classifier is making on the testing sample. And we know this is a good estimate of the risk, and there are some theorems showing that if you minimize this, with high probability, you're going to be minimizing the true risk. But of course, as I said before, we can't compute this because we don't have the true labels. So what we did instead was to use a different score. Instead of using this, we use this other score, which is actually quite simple. So if we focus here on the inner part of the sum, this is just looking at the proportion of mistakes expert J thinks classifier F is making. So you look at how many mistakes each of the experts think that classifier is making, and you average all these proportions. And that's how we attribute a score to classifier F lambda. And then we will look for the classifier that minimizes this score instead of this score because we can't compute this score. And then, well, we proved the theorem here. I won't go to the details, I won't have time for that. But it essentially bounds how far our score is from a monotonic transformation of the true risk function that we can't compute. Okay? And a consequence of this probability of this theorem stated here in a loose way, is that with high probability, the classifier you get by minimizing our score is the classifier you would get if you could minimize the true risk function. Okay? So this theorem is showing that our score is really valid in this sense of giving the best classifier. Of course, this is really loosely slated, but that's the general idea. So to show an application here, so as I said, we had the data set we are interested on had 1,600 galaxies, but it had 2 or 3 astronomers. So as a proof of concept, the astronomers did something interesting here. So they got just 200 of these galaxies, and for these 200 samples, they asked 42 astronomers to evaluate each of them. So we had a huge table, and using majority rule on these 42 astronomers is pretty much going to give us the true labels, because there are a lot of astronomers, and most of them are actually very good astronomers. So we considered that for this small data set, we had the true labels. So what we did was to choose 3 astronomers at random, and we pretended we just had these 3 astronomers, and used our methods only on these 3 astronomers and compared to what we would get if we had the true labels. Okay. So here are some results. I guess it's kind of hard to see from there, but the first plot, what it's showing is the red curve is showing how the estimated risk we can't estimate in a real data set because we would have only 3 astronomers, how it behaves as a function of the prior hyperparameter. Okay? So the best model according to red is this model here, is this value of lambda. And of course, we can't compute the red curve. So what we do instead is to compute the blue curve, which is our score. And you can see that the behaviors are really, really similar to each other, which is what our theorem predicted, right? In particular, if we minimize the blue curve, you get exactly the same thing as when you minimize the red curve. So really, the blue curve, our score is giving us the best model in the sense I described before. Okay, so this part of model selection is really working well. Now here I'm comparing the performance of 4 different classifiers. So this is our model, and this is the estimated risk. So this is our model. This is its estimated risk is about 20%. This is the same as our model, but with a flat prior. So if we don't add information in this sense of using a flat prior, we would get actually predictions which are much worse. Okay, so what this figure is saying is that you should really include your prior information here. You can make your predictions better. The third model here is the model you get if you use majority rule to get the true labels. So, or to at least try to approximate the true labels. So this is what astronomers usually do. And what it's showing is that for this data set, what they were doing was very good because it's about the same as what we are doing. And in fact, it's the same, about the same performance you get when you use the true labels, because for this data set we have the true labels. So what they are doing is very reasonable. Okay, so they did something very nice. For other data sets we've tried, well, there are all sorts of behaviors. Most of the times this is actually not very good. But for this problem it's very good. And one of the reasons why it's good is because astronomers, they are typically, for this data set they were typically very good. And they were about the same. So what I'm showing here is a box plot for each expert. So there are 42 box plots. And on the y-axis we have a parameter, which is the probability that that expert makes a mistake on a new galaxy. So it's a parameter, and what I'm plotting is the box plot of the MCMC samples. Okay? So what this is showing is that there are 2 astronomers which are almost as good as a coin flip. Okay, so they were making a lot of mistakes. It was better if you could get a coin flip, you would get the same as these 2 astronomers. But most of them, they are reasonably good, and there are, I don't know, like 5, 6 astronomers which are, very, very good. Unfortunately, we didn't have the labels of who astronomer was whom. They wanted to keep some privacy on this data set, so we don't know if this makes sense according to I don't know, if this guy, for example, is really an expert on the field or something like that, but that would be something nice to see. So to wrap up, in this work we developed a Bayesian model for crowdsourcing. We showed that prior information improves predictions, which of course That's obvious. So you should really use meaningful prior information if you have. Then there's the question of how much prior information should be introduced. So in a sense, that's how should you choose lambda, the precision of your prior. And for that, we developed a model selection tool, which is not really the subjectivist Bayesian approach to this problem. Okay? But although that's not the traditional subjectivist approach, I think it makes a lot of sense. In particular, I think data splitting is very natural. It has a huge convincing power. So if you show the astronomers, oh, this classifier is really predicting well, this data is testing data, this has a much larger convincing power than showing that it's your true posterior distribution. In general, not only for this problem where labels are unknown. However, there's the question of what do the credible intervals mean? Because they don't really reflect your uncertainty. So the box plots I showed you in the last slide, they don't really reflect my uncertainty in a subjectivist sense, because I didn't choose my prior in a meaningful way, or at least in the traditional subjectivist meaningful way. So I'm not sure how, it would be good if you could incorporate data splitting into a subjectivist perspective, because then you could get the best of both worlds in a sense. So maybe a way of doing that would be to find priors on lambda. So you'd put a prior on the hyperparameter that make the base estimate with respect to that prior to be the estimate you get if you use data splitting, or at least approximately that. Then you could make a base estimate, a subjectivist base estimate, the base estimate you get when you use data splitting. You could unify both approaches. So yeah, that's what I had. Thank you.
Not a question, just to fill in time while Emily's footling with the IT system. So at the start you mentioned some connections with the literature. There's a literature that this builds on. I'm not sure if you're familiar with the term inter-rater agreement.
Yes, yes.
And that was really dominated by Bayesians in the 1980s and into the 90s. Maurice de Groot, Prem Goel, Bob Winkler, myself, 2 or 3 others. And you're really then extending all of that with covariates, because that was all, in the main, the applications in database error checking and things like that were free of covariates. So, there's a good historic pedigree there as well. Yeah. Bayesian, fully Bayesian.
Yeah, thank you. Yeah, that's the thing. I think that one of the first papers we found was from Philip David, but it didn't have covariates. And it's interesting because in machine learning, they sort of they wrote new papers with the models that existed in statistics 20 years ago. And, well,